Hey guys, the objective for this video is to find the pore water pressure head and hydraulic gradient at different points within our flow net. Okay, so this is our flow net from 2 videos ago. I just want to just show you what I need to clarify. That was not meant to be point B there. Point B is meant to be down here. Okay, so what we want to do is we want to now find the head and pore water pressure at point A. Okay, so what do we know? We know that the head value at this EP, let's call this EP1, EP subscript 1, this EP, the head value we found before, the head at, that's point B, is 3 meters. Head B is 3 meters, okay? So this is 3 meters. So I just need to get the focus right. Okay, much better. Okay, so the head at head at EP1 is equal to 3 meters, and we know that the head of this EP, which would be 1, 2, 3, 4, 5, 6, 7, 8, the head at EP8 we know is the head at A, which is 0.5 meters. Okay, so this is 0.5 meters. So now what we're going to do is we're going to find the head value at each of these equipotential lines, and it's very easy. All it is the head. So we're going to call this now the change in little head. Okay, this is what I was talking about before. This change in head is the change in head from EP to EP. Okay, and that's going to be uniform and consistent for every drop. Okay, so the change in head from one equipotential line to another equipotential line is the total head difference on the number of EP drops. Okay, so in our case, our total head was 2.5 meters, so this is 2.5 on top of the number of equipotential drops, so that was n subscript h was 7. Okay, so 2.5 on 7, we get around 0.36 meters. Okay, so what that means is every time we move from one EP to another, we're dropping off 0.36 meters. So the equipotential at point 2 would be 3 minus 0.36, which is 2.64. Okay, so the head value at this equipotential line is 2.64 because we've dropped off, we've changed by h. Okay, we're now going to go again, change by another h. So the equipotential here would be 2.64 minus 0.36. So it's 2.28. So EP3 is 2.28. Once again, we're going to subtract another change in head to get to this equipotential line. So EP4 would be 1.92. EP5, this equipotential line would be minus another 0.36, which would be 1.56. EP6 would be minus another 0.36, which would be 1.2, and EP7 would be minus another 0.36, which is 0.84, and finally EP8 would subtract another 0.36, which would get us back to 0.5. Okay, I've gone in this direction, you could have gone in this direction, so we could have started at 0.5 and added 0.36. So we could have gone change in h by adding it, so 0.5 plus 0.36 would take us to 0.84, okay, or 0.86 roughly. So you can go either direction. Just if you go this direction, you're going from a high head to a low head, so you're obviously going to be subtracting off to get to a lower number. If you were to go from this direction, you would be adding a head because you're going from a low number to a high number. Okay, so we just use this formula, change in small h, which is the head drop from one equipotential line to another equipotential line, is equal to the total head difference, which we found earlier as 2.5 meters, divided by the number of equipotential drops, will give us the small change in h, which is the head difference from one equipotential line to another equipotential line. We can once again draw this in 2 ways. We can start from the highest head to the lowest head and subtract equipotential changes in head, or we can start at the lowest and add changes in head to get back to the highest. Okay, either direction won't matter. Okay, but that essentially gives us the head at every single point. Okay, and these equipotential lines represent points of equal head, as we've discussed. So now we can find, if we want to know the head value at A, so at A, the head at point big A would just equal 2.28. Okay, that's the head at point A. It's at equipotential line 3. So it's 2.28 meters. Okay, if you didn't want to go and like plot every single point, what you could have done is we could have found this by going the head at A equals the total head minus how many drops? We've dropped 2 drops. So minus 2 change in H, which would equal 3. Sorry, it's not big head. This is just the head at point at the top. So that would be 3 meters. So 3 minus 2 times change in head is 3 times 2. Our change in head we found to be 0.36. Okay, if we go 3 minus 2 outside of 0.36, we get 2.28. Okay, or we could have gone ahead at A equals, starting at this point, it would be 0.5 plus, so 1 increase, 2 increase, 3 increase, 4 increase, 5 increase. So plus 5 times the change in head, which is 0.5 plus 5 outside of 0.36, which would equal 2.28 meters. Okay, around 2.28 meters. So you can do it either way. I just wanted to plot every single point for you to show you graphically what's going on. So now that we know the head at A, we can find the pore water pressure at A. So we know the formula, head equals Z plus pore water pressure on gamma W. Okay, so we can rearrange this equation to get pore water pressure equals H minus Z outside of gamma W. Okay, so all we need is this Z term. So what is Z? Z is the distance we're at. So it's also important to realize from our datum, right? We've defined this as positive, okay, which means that if we were to go down, we will be going down negative, right? So from our datum, point A, so if I were to dash this across just to get a scale, okay, so we would scale this off. Point A is around roughly 5 centimeters. So point A is roughly 5 centimeters from our datum. Okay, I've come down from our datum 5 centimeters. So, and we know that our scale is 1 centimeter equals 1 meter. So Z is minus 5 meters. Okay, because we've gone down 5 meters from our datum, because this is negative, this is positive. So the pore water pressure at A would equal the head at A, which we found to be 2.28. So 2.28 minus 5 outside of 9.81, which is the gamma of W, which we can then find to be 2.28 plus 5 times 9.81. Our pore water pressure is 71.4 kPa. Okay, so that would be our pore water pressure at the point A.